Over large distances, the universe is governed by the gravitational force. In physics, the action of a force is the cause of motion or of any form of change. Complete rest is possible only if no net forces are acting. One scenario in which this can happen is the absence of any matter whatsoever, a state called vacuum. But matter quite obviously does exist, and just by its mass it causes gravitational forces on other masses. To realize motionless states of rest, at least approximately, all acting forces must compensate each other. In addition to gravity, there are the electric and magnetic forces to be considered, as well as two kinds of forces called weak and strong interactions, reigning in the realm of elementary particles. While the electric force is easily compensated over large distances by the existence of positive and negative charges, mutually neutralizing each other, the forces that come into play in the interior of nuclei act only at extremely short range. What remains over long distances is gravity alone. It rules the general attraction of masses and energy distributions in space, and thus dictates the behavior of the universe itself. In contrast to electricity, there are no negative masses. Gravitational attraction cannot be fully compensated. Once massive objects such as stars or entire galaxies form, the resulting gravitational interaction dominates all that happens. The facets of this commonplace force, often ignored in recent research and yet, in cosmology and black holes, giving rise to a rich variety of exotic phenomena, are the topic of this book. Newton's law of gravity, distant action and a fatal flaw. The first general law of gravity was formulated by Isaac Newton. As is typical for many important steps in gravitational research, this theoretical development required a unified view on well-known phenomena on Earth, with a long list of intricate observations of objects in space, the Moon and some planets. The latter was accomplished thanks to technologies that, for those times, were highly sophisticated. Conversely, such research has spawned the development of new instruments. Combining fundamental questions and technological applications in many areas of science and in gravitational research in particular is a success story that continues into the present day. Even before Newton, the initial untidy flood of data, as it was accumulated by astronomers such as Tycho Brahe, Johannes Kepler and many others, was ordered into a model of the solar system. Since Nicolaus Copernicus and Kepler, this model has largely held the form we know today. Planets orbit around the Sun along trajectories that, by a good approximation, can be considered as ellipses or slightly oblong circles. But what is propelling the planets along their curved tracks? From common observations, we know that a force is necessary to keep a body from moving stubbornly along a straight line. How can one describe or even explain the required force in the case of the planets? Newton's groundbreaking insight, the existence of a universal force of gravity causing not only the motion of all planets around the Sun and of the Moon around the Earth, but also the everyday phenomena of falling objects, is impressive. It is an excellent example of the origin of scientific explanation, not an answer to a why question in the sense of an anthropomorphic motivation, but a plethora of complicated phenomena, unrelated at first sight, reduced to a single mechanism, a law of nature. Newton's mathematical description of the situation is very compact and highly efficient for predictions of new phenomena described by the same law. In the case of Newton's law of gravity, the unfathomable power of theoretical prediction has repeatedly been employed. For instance, to find new planets via small deviations imposed by their gravitational pull on the trajectories of other planets, or in planning modern satellite missions. Such success stories, in which an elegant mathematical description explains and predicts a multitude of phenomena, can be found throughout physics. they are indeed the landmarks of its progress. Reliving such insights is often so gratifying that scientists employ the term beauty, a pragmatic kind of beauty whose core, the mathematical formulation, can be seen only by the initiated, but which in its concrete successes can also be appreciated by outsiders. Footnote. Other striking examples are provided by the main theories covered in this book, general relativity and quantum mechanics. These theories started perhaps more controversially than Newton's, for they came at a much later stage and were tasked with explaining more subtle phenomena. In these, as in other cases, it is almost shocking to realize that purposeful mathematical manipulations, pure thought, can so closely correspond with nature. So often, observations have been preempted by bold predictions, for instance of elementary particles envisioned before they were seen, following purely mathematical symmetries. Then again, theoretical visions so often turned out to be incorrect. But by being right much more than once, theoretical physics has abundantly shown that it did not just have a lucky strike. Its attempted predictions are indispensable in guiding observations and leading physics to new frontiers. Being granted confirmation of one's own ideas, even if they are rather minor, is every theorist's dream, though only few can have success. It is as if one thinks one is playing a game of chess, only to find oneself leading an actual battle. End footnote.